All right, so I'm here to talk about the NASA Marshall Space Flight Center Solar Instrumentation Program, which has a lot of programs, I should say, and it has I'm just showing the core group of people. Jonathan Certain has flown the COOP recently, but this is just the core group, and there are many, many more. This consists of project managers, budget analysts, our support, and of course a lot of engineers. So Marshall is an engineering center, and that's why we really like to push the boundaries of the technology that goes into solar instrumentation. And so I have divided this talk into basically two sections. The first section, I'm going to talk about everything but High-C2, and the last section, I'm going to show the first results, or at least the preview of the first results from High-C 2.1. All right, so these are our programs that we have: sounding rockets, observatories. We have COSY, which is a proposal right now, and then we're also building a lot of cameras and optics. And I'll talk about each one of these in turn. Let's start with the sounding rocket programs. Just to mention that the SUMI sounding rocket instrument was flown a couple of times, and that really started the whole Marshall Solar Sounding Rocket Group. But I'm going to start with the targeted science from all of our sounding rockets. So basically, these are the phenomena on the sun that we are targeting. So High-C looks at the corona, High-C2 looks at the lower corona, High-C1 looked at the upper corona. MAGIX is targeting the reconnection, especially in nanoflares at the base of hot coronal loops. Then we have the CLASP sounding rockets. Those instruments are spectropolarimeters, which are focusing on the chromosphere and measuring the magnetic fields there. SUMI was targeting the chromosphere and the transients. High-C, the instrument itself, is the high-resolution coronal imager. It was a telescope that was designed to be capable of about 150 kilometers in spatial scales, about 0.1 to 0.13. It requires high rocket through rapid CCD readout duration, and this is a camera that we built ourselves out at Marshall, except for the High-C one. So we read out an image every 2 seconds, and then we also have storage on board. So High-C1 was launched out of White Sands, New Mexico in July 11, 2012. It lands about 70 miles downfield out in the very hot, scorching desert. And it's metal, so when you go to pick it up, it's extremely hot. You have to wear very thick gloves. You can't touch it. So here's an image of it with its parachute out in the desert. And the recovery team goes out there on the helicopters to go bring it back. The data for this mission is available via the VSO, and there are guidebooks there as well. And we also have a website, highc.msfc.nasa.gov, that you can go get data from. All right, so here is a nice movie that Amy Weinbarger put together, showing this is from SDO, and then zooming in on certain regions, and you can compare AIA 193 with High-C, and this will loop through certain regions in the field of view. The bandpass for High-C1 was 193, so about 1 million and 10 million Kelvin to 20 million Kelvin. We have 26 publications for 5 minutes of data on this one, so it was extremely successful, and you can go and look at the publications on the website. The science highlights were braided loops triggering energy release, and there will be a movie of that in just a second. That was published in the Certain et al. Paper in Nature 2013, so here you can see these very nice small stranded loops compared to AIA. There are also subflare triggers, nanoflare heating, loop substructure, Moss dynamics, a lot of Moss dynamics. Even penumbral jets, and of course flows along the filament threads, and even MHD waves, even though we only had 5 minutes of data. So this is a big difference in the resolution you can see with the High-C data. And here is just a nice summary figure, and this is from the Nature paper showing the differences in the scales between High-C and AIA. Now, of course, we can't get the field of view that AIA can, but we can definitely beat it in resolution. So the points of contact for High C1 would be Amy Weinbarger, myself, or Ken Kobayashi, and Ken is our instrument scientist for pretty much all of our rockets. Okay, then moving on to CLASP. Class 1 is the Chromosphere Lyman-Alpha Spectropolarimeter. It consists of a Cassegrain telescope, some rotating wave plates, also a slit jaw and slit jaw camera, and a diffraction grating, and then polarizers. So the objective is to use the polarization to infer the chromospheric thermal structure in the magnetic field. Basically, they wanted to measure the Hanley effect to measure the magnetic field in the chromosphere for the first time. This one requires very accurate calibration for this type of instrumentation and very advanced thermal modeling. It was launched out of White Sands as well in 2015. And so here is a nice video of the rocket launch. I'm going to skip ahead a bit. So the nice thing about this particular movie is that you can see where the rocket is in space. You can see the team in here, and in a second the data will pop up at the same time. So as it gets stable, Amy is repointing the image, and you can see how stable these rockets are. And this is actually why we choose White Sands in particular, is because they have the Sparks guidance system. It's easy to use, and we can go out and easily retrieve the sounding rockets as well. So I don't know if you caught it, but there were a bunch of high fives all around. So Class 1 was quite successful. There have been a few papers out already. The initial results were that they did measure a few % of polarization in the wing and also in the core. There's a clear center to limb variation in the wing of the Q to I. And this is essentially consistent with the model predictions. So the conclusion was that they did measure the Hanley effect, even if it was a small effect. The points of contact for that are Amy Weinbarger and Ken Kobayashi. Now there's Class 2, which is scheduled to fly this spring, so very soon. What they've done is they've changed the wavelength from Lyman-Alpha, so it can't be the chromospheric Lyman-Alpha spectropolarimeter anymore. It's now the low atmosphere spectropolarimeter. They've changed it from Lyman-Alpha to the magnesium 2 H and K, which is also another set of magnetically sensitive spectral lines at about 280 nanometers. And this is to basically explore which of these lines is best for a free flyer mission and how routinely we can get these measurements of the magnetic field in the chromosphere itself. The PI for this one is actually David McKenzie. The project scientist is Laurel Rockmeller. And again, Ken Kobayashi is very busy. All right, skipping ahead a bit, we're going to go on to MAGIX, which is scheduled to launch this August. So CLASP will launch in the spring, around April. And then a few months later, we're going to launch MAGIX. But there are a couple of different teams. MAGIX is the Marshall Grazing Incidence X-ray Spectrometer. It's a very ambitious telescope. It consists of a Walter Type 1 telescope at the beginning. It has an effective focal length of about 1 meter. It has a slit jaw imaging system, which is actually pretty novel. It also has a spectrograph filter, and then we'll be only using a portion of the total telescope itself. That light will be incident onto a grazing incidence grating, and then that will be fed into the detector. So if you've counted, there are 1, 2, 3 different grazing incidence mirrors that we're actually having to align, which is extremely difficult because we're looking at a very high resolution imager in space and in spectra. So this has been a challenging instrument, but we're coming along very well. And we actually develop and build those mirrors at Marshall. They're very high resolution imagers. Okay, so the science goal is to determine the frequency of heating in active region cores, basically trying to distinguish between sporadic or nanoflare heating versus waves. So this is a simulated spectra of a single spatial position along the MAGIX slit. So for high frequency waves, we expect the spectra to look like this, and for low frequency, then it will look like this. So you can see we have very high spectral resolution in the softer X-rays in this wavelength band. And this is also the simulated MAGIX spectra. This is what we expect to see if if we have the wave heating versus the nanoflare heating, and there's an especially big difference in the iron 20 line right here. And so that's what we're going to be looking for. And that's just one of our science goals. The points of contact for this one are Amy, myself, and also Ken.
Sabrina, what's the energy resolution?
Oh, ask me afterwards. I can look it up for you. All right, so those were mainly focusing on the lower corona regions, but we also extend, our instrument programs extend from the photosphere all the way out to about 3 solar radii, and that's with Hinoday and COSY. Yeah.
Why don't you take your telescopes to the station?
That's coming up. That's a great question. I love it. Thank you. I didn't plant that at all. But first, the Hinoday satellite, which people here actually work on and help to run and operate. So Hinoday consists of the Solar Optical Telescope, which is SOT, the Extreme Ultraviolet Imaging Spectrometer, which is ICE, and then the Soft X-ray Telescope, which is XRT. And so we've been observing with Hinoday for about 12 years now. The project is managed out of Marshall. And this is actually a very nice Hinoday SOT filtergram image, or a set of images from one of our focused mode observations where we take and just observe an active region for almost an entire week. This was implemented a couple of years ago just to kind of save on our observations cost, our operations cost. But we've been able to, we have a nice long baseline study of solar variability, especially with XRT, because we can see the full disk in X-rays, and you can see how it has evolved. And here's another nice image showing the difference in the cycle. I love this one from Hinoday ICE, because ICE is a spectrometer. It takes a couple of days to get a full disk image like this, and this is narrowband data of the entire disk. And this is combining, I think, 3 different wavelengths, which is really nice. Here's Hinoday XRT going from solar min to about solar max. Here's another nice image or movie of the small magnetic fields in the weak magnetic fields on the solar surface from SOT. And here's our example of the spectropolarimeter data from Hinoday SOT. So we don't have the filtergram imager anymore from SOT, but we are upticking our production with the SP, which has actually been quite nice. We get a lot more high-resolution images from it. So the points of contact for that are myself. I'm the project scientist for the US, and then the program manager is Stephen Elrod. All right. Now, to get back to your question about COSY, we have proposed and are in the process of reproposing this Mission of Opportunity instrument for the International Space Station. The idea is to have this novel imager to have a coronagraph that can actually observe the disk and the corona at the same time, out to 3 solar radii. And we can only do this in the EUV. We would like to be able to test this out before putting it on a free flyer, but we can't test it on a sounding rocket. There's just not enough time because you do have to capture the CMEs. And there's just a big cost gap between sounding rockets and Explorer missions. So we're doing this with a Mission of Opportunity and trying to put it on a location on the ISS. The first time we proposed it, we did win Category 3 funding, which is to basically mature some of the technology. We've gone back and done that, and now we're reproposing it again. But here's the basic idea, the premise of why we want to do this, which everybody here is probably very familiar with. There's this big gap in our observation space, and many of us would like to fill this gap. And this imager is very complementary to a lot of other missions that I've seen. So it's not a standalone mission. It would be great with a white light imager, et cetera, et cetera. The idea is to be able to connect the phenomena that we see out in the outer corona, or in the middle corona, with what we see in AIA and with even SWAP right here. So, and in one wavelength. That's a big deal, especially for the kind of science I do, which is connecting reconnection observables from the outer corona into the inner corona. And here's an example movie of what COSY will see. It'll actually see the source regions out into the corona, which is not something we are currently capable of doing. And again, oh, and this is one of the best parts. Our feed mirror to get this image also flips over, and then we get an overlapogram, and then we can deconvolve that and get density of the entire disk all at once, which is pretty cool. So the points of contact are myself, and this is actually PI'd out of SAO by Leon Golub and Ed DeLuca.
How you get the dynamic range? Is it the desensitized process?
Yeah. So it's a different kind of filter where the filter over the solar disk is actually thicker than the surrounding area.
That's in the image plane right up.
That's exactly right. Not for the overlapogram, but just for the coronagraph. That's right. That's how we get the very large dynamic range. And we use the profile, the edge of that thicker filter to our advantage to basically offset the decrease in sensitivity or the emission out in the corona. So it's almost like a filter itself. All right, and then we also develop a lot of cameras and optics at Marshall. Several of our programs, we have our cameras built in-house, and the camera for Hi-C2, which I'm going to show momentarily, was actually built in-house and has extremely low noise characteristics, and I'll show an example of that as well, which is really nice. And we're building a lot of optics, especially the X-ray optics. We're moving into that arena. So cameras and optics are being led by Ken Kobayashi and also Laurel Reckmiller and Patrick Champy. All right, now for the second half of the talk, which I'm really excited to get into. Preview of the first results from Hi-C 2.1. This was a project that was led by Amy Weinbarger, myself, and Laurel, which is kind of unusual because it was led by 3 women. And here's our science team. You might recognize a few of these, especially right here, which I don't see in the crowd. All right, so Hi-C 2 is the High Resolution Coronal Imager Part 2. This was actually launched back in 2016. The mirror was recoded to explore, to look at the chromosphere rather than just the outer corona or the upper corona. And the science goals were to target spicules, type 2 spicules in particular, and also hot active region core loops. So for Hi-C 1, we had the 193 angstrom bandpass, but for Hi-C 2, we switched it over to a 172 angstrom bandpass, so much cooler, so more like 0.6 megakelvin versus a million. There was significant improvement in the camera quality. Like I said, we built that one. And for this mission, we also have Iris, which was a big deal for us, to be able to correspond those features that we're seeing in the lower part of these images. However, Hi-C 2 had a bit of a failure because when we buttoned it back up, one of the wires actually got pinched to the back shell. And that was our final buttoning up phase after we did vibration, and we weren't able to test it afterwards. So we have wonderful calibration images from flight. So it definitely increased our TRL from our camera, but we didn't actually get any science images because our shutter didn't open. The shutter on the camera didn't open, which was really quite sad. But as you can see, our electron noise is very low in all of these different quadrants for our camera. All right, so we cleaned it up, we re-proposed it, we checked the alignment, we did get funding. We upgraded our cooling system, which was actually a real benefit. And we added a Hall effect sensor so that we could test if the shutter was opening or not, even if we couldn't shine light on the detector. And then 3.5 months after ATP, which is probably a record, we had this. And I don't have it playing yet. I just want you to pay attention to this refrigeration box, which is around our instrument right there. And watch what happens during the launch. It's my favorite thing. It just gets destroyed. What?
Is that intentional?
Oh, yeah. It's supposed to get destroyed. It gets all burned up. And then in just a few seconds, you'll see the second stage ignite. And this happened back in May 2018, so just a few months ago. We got this data, and this is what the sun looked like. We were very fortunate to have an active region that emerged during this time period, because when we were out, when we first got there, which was a month before the launch, the sun was completely blank. So we were very fortunate to have that. So obviously that was our target. This is active region 12712. It's about a 15-minute flight, and again, about 5 minutes of solar viewing data. This is what the AIA image looks like of that region. And this is the high C. So you can see a big difference in resolution. Again, AIA and high C. It's a lot clearer. Zooming in, this is AIA, and this is high C. It's gorgeous. Absolutely gorgeous. Show it one more time. Right. And so one of the people on our science team, Richard Morton, who is out at Northumbria University, who works with waves, does an astounding job at sharpening images as well. And here's an image from a sharpened version. It's quite beautiful. You can see all of these strands all through this region. And I'll pull up the AIA image again. Here. It just looks like haze, right?
Yes, but in sharpening image, I mean, you can't get what you would get if there's stuff below the resolution limit
Below.
of the telescope.
Oh, by using like a filter on it? Sure. But even in just the...
There's still, it looks like from this striking difference between Iris and the high C2.
AIA, yeah.
That you want, AIA, that you want to buy a bigger telescope.
Yes. I wouldn't argue with that. But so yes, that's true. But even without sharpening, just the straight up data, you can see all the striation.
No, it's,
Yeah.
I
Yeah.
fully appreciate what you have.
How far away from the edge of the sun is that?
Let's see. It was not very far. So that was the field of view.
You don't notice any helmet streamer on that? Or is that too low?
A helmet streamer from the disk. So yeah, no, I haven't looked for a helmet streamer. So I do have, again, that's just amazing. Okay, I do have a movie. So this is the full data set, and you can see there's kind of a cyclical pattern where it gets a little fuzzy, and there was some jitter in the rocket motion just because as it was correcting, you can see a little bit of that correction movement as it's moving across the pixels. And if you remove that, then this is what you get. You can see all of these small dynamics within the moss. And this is even on a projector, so you can imagine what it looks like on my screen itself. There's even these very tiny threads that you can watch move, and there are flows going along those very small threads. There are even some nice little nanoflares or microflares down in this region where there is flux emergence. So there's a plethora of science opportunities there to look at. And here we're zooming in without the jitter. Again, you can see these very small threads that are fading and moving. Now, I don't know if they're actually cooling through the bandpass or if they're actually moving. That's something that we're looking at as well. But there's a lot of moss dynamics in here. And even that little microflare. Actually, when we were in real time getting the data down, which we only get about every 2 or 4 images at a time on the screen in full resolution, we weren't sure if it was even moving or anything was happening until we saw this little brightening. And so the operations team is separated in a room from the actual visitors that are in another room, and we could hear them all going, ah, as we did the same thing. Because they weren't sure it was moving either, or actually taking images. So what makes this image work, or this instrument work, is because of the high spatial resolution, of course. Also the high temporal resolution. We get images every 4 seconds. And low noise camera is very important as well. But I think most important are the coordinated data sets. So we did a lot of coordination with several different observatories in space and on the ground. Notably was Iris. So that's what we were that was the requirement. So IRIS did have a subset of observations for us. We got images in the 1330 and the magnesium 2K. And this is so that we can look at the flows from the chromosphere up into the corona. Here's the field of view of IRIS, and you can see that Bart DePontu nailed the target for us. Here's a nice movie from IRIS. And there is this beautiful flux emergence region right in the middle of our field of view, and the slit is right over it. It also captured a lot of these nice fan loops up in the top as well. So we're super excited about that. Here's what it looks like in 1440. And you can see the difference in some of these features, how they look in IRIS versus how they look in high C. What's bright in IRIS is oftentimes dark in high C, which is really interesting. Again, this is another one of those interesting phenomena where it's kind of backwards here, where IRIS is dark and it's bright in high C. And here's IRIS 2832, comparing the phenomena. And of course, we have a raster set right across that nice flux emergence region. So this is high C, the 172. We have silicon 4 and then magnesium 2K. Also, we have the Hinoday coordinated data. All three of the instruments on board got data for us, which was fantastic. So XRT provides our coronal context. ICE provides the narrowband spectra of the hot loops. And then SOT-SP was getting the magnetic field for us underneath. So here are some example images from XRT and then ICE, and also the SOT-SP profiles. And it was really fortuitous that our launch happened when it did. I'm not sure if anybody was aware, but ICE was off for a couple of months. It just randomly turned off. It was probably just a single event upset, but it turned off during a bakeout. So we were very careful about bringing it back up, and it took a couple of months. And the week before we launched is when it came back to full operations. So we were able to get a full data set, and it had been baked out. All right, and then we also had several other coordinations with NSO, New Star, BBSO, Owens Valley, and we tried to coordinate with SST, but that wasn't as successful. All right, and so thanks to Kevin Reardon, we have some beautiful data from NSO, the Ibis instrument. Here is the Ibis Mosaic in the calcium 2. And here's what it looks like compared to high C2, which is amazing. It's almost very similar resolution. I love it. So these are very easy to compare. And zooming in on a couple of these regions, Kevin, thank you for these. I really appreciate these slides. So this is the high C172 image, and this is that center portion from the calcium 2 image. And again, this is with the H alpha, and what it looks like, that field of view looks like an H alpha. And this is, so it's 0.098 arc seconds per pixel, and for high C 2.1, we're at about 0.13. So very similar. And this is what it looks like with comparing the two. So this is obviously underneath everything that's on the high C2 field of view. And zooming in on that same field of view, there's the high C2 image, all that nice moss that is very dynamic. And you can see this as well in the H alpha.
So if I could just observe something that image, the dynamic moss that you just pointed to seems to kind of have features in it that are really separate from Ibis, in the sense that it's a much more muffled, smaller scale appearance. And that, do you think, due to coronal physics? In other words, are we seeing the effect of what we're looking at here is heated plasma close to the top of the chromosphere?
From here, right?
No.
Okay.
Well, that's what
Yeah, at the very base of it, yes,
So,
yes.
I mean, is that telling us something about, independently about the scale upon which heating is going on within the corona? So that the cross field kind of dimensions of which energy is deposited and then immediately conducted down to the static emission. But if it is, then that's the impression I get when I look at those two. I see coronal physics on tiny scales bringing energy down, and modeling the structure more than in the H alpha, which is maybe lower down and not subject to the same production.
That's right. So I think you're hitting the nail on the head, but this is something that, this was kind of the purpose of this mission and the reason why we chose this wavelength. And so the full initial science results will be presented at AGU. Right now I'm just kind of giving the preview of what the images are, but yes, this is something that we want to look at, is this cross-scale comparison of the energy flow and the dynamics. Absolutely.
What is the scale of that multiple appearance there? Is it half a millimeter? Is it 0.3? Is it 1? Is it just a matter of trying to give an idea?
Do you know how big this the field of view was? What was it?
It's about 100 arc seconds.
About 100 arc seconds.
Those are close.
So yeah,
Maybe a few, maybe a couple hours seconds.
maybe at most, yeah.
Okay.
Mhm.
Thank
No, please do. All right. And then we also have NuSTAR coordinated data. For those of you who don't know what NuSTAR is, it's actually a hard X-ray astrophysics mission that has very high sensitivity. And it's kind of hard to get a coordinated data set with them to look at solar features, because it has to be the right sort of conditions on the sun for them to be able to actually observe the sun. So there were 5 orbits dedicated to solar viewing on the day of the launch, and this was primarily targeting the field of view that we were looking at. And here's what we got. So we do have some nice high sensitivity hard X-ray images from NuSTAR, and we're going to be looking at nanoflare heating by comparing these two types of observations. And this is headed up by Lindsay Gleesner and also Jesse Duncan out at Minnesota. So we also have BBSO, and that was coordinated by Ben Chen, and I also have special thanks to several other people that helped to coordinate on launch day, because it's not easy. So the science topics that we're pursuing with the High-C 2.1 data are obviously the thin stranded loops and what are the width variations and how do they compare to the High-C 1 data in the 193 channel, which was above and hotter. Also, of course, looking at the flows between the transition region and Chromosphere and Corona, and Iris will feed a lot into that. Looking at spicules, nano and microflares, the Moss dynamics, and also flows along the loops, especially the ones that were nice and threaded, real thin ones. Also some waves in there. It's a little bit harder to do that with this data set than it was with the High-C 1, just because we have to take out some of those jittered image sets, but we can get them in there as well. And even mini jets, and that's something that Navdeep Pinisar is looking at right now. So here's just the AGU plug. There's going to be an AGU session highlighting suborbital events or results. So in particular, High-C and also FOXE3, which is going to be launching hopefully in a week now. So we expect to have High-C 2.1 science results in that session, several different talks. So if you're interested and you can make it, please do. Oh, it's a hard X-ray imager in high resolution. So it's also a sounding rocket, and it's flown a couple of times now. So the POCs for High-C 2.1 are Amy, she was the PI, myself, Laurel Rackmeller, and also Leon Golub, and I think this is one of my favorite pictures in the world now. All right, so thanks and stay tuned, and I'd be happy to take any more questions. Yeah.
What are mini jets?
Mini jets, okay. So I assume you know what jets are, and these are just the very small filaments that are within an active region, so they don't comprise a full active region or a full jet like you would think of in the polar regions. They're actually very small filaments that erupt. There's at least one paper, and I think there are a couple by Alphonse Sterling and Navdeep Pinisar and also Ron Moore talking about it.
What sort of dynamic range do you get out of, say, a pixel in the High-C camera, let's say from the dimmest, quietest quiet sun to the brightest?
I haven't looked at that, but that's actually a very good question. That's something that we should do to characterize the camera. Yep, you're right, dynamic range. I'm not sure though, but I'll look at it. So that's a good question. So we have a science team that are working on the topics that I listed right there, but the data will become public right about AGU time, and that's what's kind of getting us going and why we need to finish up some of these things, because after that, then anybody can do it. So we would love to have people from the community publish data on publish papers on this, just like with IC1 data. So yeah. Yes.
How deep in the chromosphere can you actually see at 171? Because you'll have neutral absorption from helium, neutral helium, ionized helium, and neutral hydrogen. So you're sitting in the continuum of all those species, which are prevalent in the chromosphere. So there must be some horizon below which you can see.
That's true. I don't know the actual depth, but I do know that we're seeing some of the chromosphere, and I believe this is from the oxygen line, and this is coming from BART. I'm not an expert on that, but there is some overlap in the chromosphere, also with the 193 channel. So yeah, it's there, but I don't know how deep it is. Yeah.
Can you say anything more about the magnetic Hanley effect measurement of those magics?
That was from CLASP. That was from CLASP. CLASP is the Spectropolarimeter measuring the Hanley effect.
Yes.
Yeah.
What kind of magnetic fields did they see? This is we're talking about the Lyman-Alpha.
Yeah. I was afraid somebody was going to ask me about CLASP because I am not on that mission, so I'm not an expert on that one. But the person to ask is Amy Weinbarger or David McKenzie, and they'll be able to direct you to everything that you need. But for the first one, I would ask Amy. Yeah. Yeah.
What is the aperture of high C?
The aperture, the size of it. Don't think I actually put that. It's about yay big. The primary mirror is about yay big, so it has to fit in the 18-inch volume, so it's less than 18 inches. I think it's around 10 actually.
So the resolution is limited by this optics?
Yep, it's limited by the having to be constrained within the sounding rocket volume. That's right. Yep, all of it. Mm-hmm. For high C?
Yeah, because you're observing at 17 angstroms.
That's right.
So the fraction of that chapter, that has to be substantially less than the size.
So we're limited by the camera pixel size. We're limited by the size of the instrument itself, the focal length that we can get out of the mirrors, the filter. Coating the actual primary mirror and the surface smoothness. So there's several different things that are limiting us on it. Yeah. Okay. I'll take that. Yes. Yeah. There are several different ways that we could improve it, but I mean it's working. So the idea is to show that this is worth doing, and obviously it is.
Even at this level, then you should see a measurable change in the resolution, in the brightness distribution from IC from AIA. And so is there any limit, if you were to plot the image contrast versus resolution, is there any hint that you're reaching a fundamental length scale?
So actually, Amy published a paper from the High C1 data saying that we're getting pretty close. At least based on a similar sort of assessment, yeah.
That really surprises me because I don't know what the fundamental scales are of the heating process that then is conducted down the field line that makes that whole tube light up. But the cross field structure could be, rather the structure that dissipates energy, a little bit of reconnection to the nanoflare or something. That's not defined yet, and I think it must be probably make an argument as to what that body. What I'm trying to get at is if I take two tubes and I twist them up a little bit and let them connect, what is the scale difference between them? And so
In the corona, or at the foot points, or at the top of the loops?
In the corona, where the some of the twisters conservers go up into the corona, so if you're going to heat the corona, you've got to do it over a large volume. So you could take the total amount of energy in an nanoplate over 24 hours and divide it by what you think the processes are, and figure out the length. And in my mind, I don't know why you'd expect it to be close to, say, or close to 100 kilometers, let's say 100 meters. I mean, I just know in physics that would do that, say, for instance. So it would be surprising to me if you really think you get to the fundamental scale pretty closely.
Well,
If you think you are, you have a fantastic case to do a something that's 3 or 10 times the resolution and prove it. That would be
well,
an
how well
absolute
will
breakthrough for plasma and solar physics. I mean, really.
will DKIST get as close to this?
We're going to be struggling with image quality all the time. Not sure we'll be able to interpret data on the disk, let alone in the corona very well on the first slide.
Okay.
I mean, that's best to stick with it. And it's over here that might disagree.
Actually, I
Well, I know there have been several arguments against having any higher resolution, but
I don't buy any of that. I think you know,
we need more minutes of data to be able
Cortez would
to.
never have made the journey if we didn't suspect there was something out there. And I think until you reach that limit where you can prove that you can't get any more information out of the data, that's such a pedantic way to go about it.
That's true, but even with Amy's paper showing this fall off, I still think we need more data to be able to actually show.
I would love to see you be able to do, I mean, for 10 times this resolution. Just go for it. Let's be done with this argument.
We could. I mean, we're doing this on a sounding rocket budget, right? It's very small, relatively speaking. It's not small in the grand scheme of things.
That's why we call it research.
Yep.
It's no guts, no gain.
Yeah, no, sounding rocket program is great. It's where we have the highest risk and the highest reward. So what my favorite thing about it is that when you see a picture on the screen, this group is the first people to ever see this, right? Ever. It's fantastic. Yes, I did. Thanks to Amy and Twitter. Yes.
Almost live to Facebook feed of them observing this.
It was a lot of fun.
With a smile the size of a,
That's right. So right after we got the instrument back, Diana Bebout got all the data off for me. They handed me the hard drive, and I carefully locked myself away in a closet so that I could get the very initial calibration out so that I could show everybody the images at the dinner. It was really fun. Yep. Thank you. Yeah, thank you. It was a lot of fun. So, and I love this program. It's nice to be at an engineering center because you have all these engineers at your disposal to help out with really pushing the boundaries. So I like that about Marshall. What was that? Actually, we're always looking for partnerships too. So if anybody's interested in hardware or software or science, contact us.
So I'm coming back to my question. Why can't you take one of these rocket experiments and just attach it to the space station?
Okay, I see where you're coming from.
Structure that survives the launch on one of these god-awful sounding rockets. You should be able to put it into Elon's Dragon capsule
Yes.
and ship it up there.
Okay, so I have a couple of different responses to that. First, yes, the sounding rockets are they're a rough ride. And I don't know if anybody saw the probe launch, which is liquid propellants. I was out there. I have the tattoo. It goes really slow, whereas these sounding rockets, which is a lot of G-forces. So yes, it is a god-awful launch or ride. But we can't put these giant instruments onto the ISS primarily because they're very difficult to point. The COSY instrument is just about 1 meter long, and it is it's already a handful to try to point on the ISS. We have looked into putting in an interchangeable platform onto the ISS so that we could put like 4 different instruments at a time and then have that platform point at the sun all the time. Then we can just take them out and put a new one in. So that's something that Marshall has tried to pursue, and maybe we'll pursue this on the Deep Space Gateway actually.
So
But it's the size, it's the volume. The Dragon capsule does have a volume constraint, and so you have to have big waivers. These are 2 meters long, and you can't fit them into the capsule.
So I invite you afterwards to go upstairs and look at the engineering model of the coronagraph that flew with Skylab.
Right, but they were not constrained by the Dragon, right? To get up there, they had a lot more volume to be able to put up in space at the same time. Am I not right? Yeah, and anything that went up on a shuttle, that they were unlimited in space. So afterwards, but now we have this very small volume that we can actually take up there. So we're really constrained by mass and volume.
Quick question, how long is Elon Musk's Tesla?
Didn't he say infinity to begin with? And then it became 100 years or something?
Well, no, that was a heavy, that's quite a special fairing too, a big fairing.
Oh, getting a pointing platform on that would be difficult.
I'll just take the test.
That's right. Yeah. No, but so the ISS is a great resource because it has almost unlimited power, but we are limited in the size that we can put up there. And it's difficult to point these things at the sun with precision. And for something like high C, it wouldn't work because you have to have incredible precision for that. We're already pushing the boundaries on the spark system, the guidance system for the sounding rockets as it is.
And the problem is that the ISS is moving quickly, right? And so you have to track quickly.
Not only just a track, because you can predict that, right? But it's doing this, and then you have a vehicle come in and everything jerks around, and you reorganize what's on the structure. There's contamination issues. It's a challenge. It's a challenge. It's a great resource, but it's a challenge. Yeah, but it's jitter. There's a lot of jitter.
You could probably use active optics. I thought Hinode has an active sector. I think so.
Yes, and so on COSY we also have a tip tilt mechanism, so we do have active optics on there. But even to that point, and so, but also we're limited by budget because it's a mission of opportunity, right? You can only do so much. Whereas Hinode is a STP, it's a probe. Yeah.
Alan Gary was working on some spherical feather probes for the UV.
Yeah.
Did he do that?
He-
Jonathan talked about something like that. That's not. There's no development.
Oh, I remember this conversation. That was a long time ago. Yeah, I think that really dropped after he left. Yep. Jonathan is out at BWXT, so BWX Technologies now.
I have a question. Following up on Phil's comment, do you agree with him that if you could have anything, like for the next generation of this stuff, do you agree that increased resolution is the number one thing you care about most, or do you want longer observing time, or multiple wavelengths, or spectroscopy?
So I can't narrow it down to one, but I can narrow it down to two. I really need COSY. I just need that data. I don't really mind who does it, but I need that data really badly for my science. And that's one wavelength, big field of view. Be able to see the source and the outer field of view, not just a coronagraph. I can't. That's not enough. But also high resolution X-ray. So that's what I really want to do, is the hot channel. As hot as I can get, either with high C, going up to 131, or even beyond that, 108 or something like that, or soft X-rays, which is something that we're working on. The next thing that we're going to start working on beyond MAGICS is to use what we learned in making those high resolution X-ray optics and making something to succeed XRT. So XRT is about 2 arcsecond resolution, and we want to get sub arcsecond. That would make me happy.
I really like the soft X-ray region a lot because spectroscopy, you have this fantastic sort of Gabriel
There's
Ford
so much in there,
set of
yeah.
diagnostics from the hydrogen, helium, and lithium-like ions,
Mhm.
which are so unique, all packed into a fairly small wavelength range like you're talking about.
Yep.
That make an absolute perfect flare mission. I mean, SMM did some of this, but I think because you've got such clear diagnostics of temperature and density, it's so obviously, right there and accessible, and you don't need all of that stuff as well.
Yep.
I think I'm really pleased to hear you going in that direction. I must say, it's something I've been thinking about for quite a while, and I think
Yeah, this is a
resolution
great bandpass.
plus that soft X-ray region with the hydrogen, helium, and lithium-like ions is wonderful.
Yep, and we can get density diagnostics in that region, which is really nice, So so Amy's on the sounding rocket board, and something that she's kind of working towards is getting a flare campaign. So several different sounding rockets launching into a flare, which would be amazing. Yeah, solar minimum. No, and then in the next couple of years.
The solar planet it'll get funded.
Okay.
Okay,
Yeah.
I want to follow on Bill's comment, and that's sort of from the stellar side of things. We have terrific observatories like Chandra and XM and Newton that have very high
Thanks for staying around.
energy resolution in that soft X-ray band, so you can see all those lines, and they're recorded simultaneously. Now Phil mentioned SMM, which had a thin crystal spectrometer, flat crystal spectrometer, and other instruments on it. But they could only, as I recall, observe certain channels at a time, like calcium 14 or whatever it was. But 19, calcium 19, and but they could only observe sort of one group of lines at a time. But if you get the whole band pass all at the same time, you can observe the multi-thermal plasmas and multi-density plasmas that are actually present in view. So I think that something like MAGIX is really approaching what Chandra does for stars.
Yes.
Do it for the sun, and that's what's really been missing over all these years is a broad, high-resolution X-ray spectroscopy mission.
And that's actually how we often present it, is MAGIX is Chandra for the sun. Yep.
The resolution is almost the same.
We're getting there. Yep.
Oh, you need Chandra's big.
Yes, and I believe it's nested as well. Yeah.
It's nested.
Right, but we don't have to worry about the throughput when we're looking at the sun, though. Whereas Chandra definitely does have to worry about that. That's right. But we might be moving from these nickel-plated mandrels, basically, to the glass optics because we can just get a better figure because we don't have to worry about the throughput. So we don't necessarily have to nest them. Like with Foxy, they do have to nest them because the throughput is very difficult to achieve with hard X-rays. But with this bandpass, we're good. Yeah, I mean, it's gonna take the entire 5-minute rocket flight to get enough signal to integrate over. But if we were able to make a bigger optic on a free flyer and not be constrained within a sounding rocket volume, we're good. Yep. I can't wait to see it. I can't wait to see the data. But it's not going to be nearly as exciting in real time because it's a Spectra. And we're going to have to integrate it. We'll see what it looks like in the end. That's right. All right. Any more questions? Well, thank you all for the questions. I really appreciate the interaction.